Have you ever wondered how electricity turns into light? What really happens inside a bulb when you flip a switch? It feels almost magical. You touch a piece of plastic on the wall, and suddenly the darkness disappears. But nothing magical is happening. Tiny charges begin to move through metal, bumping into atoms along the way. Those bumps create energy changes, and somehow that energy becomes glowing light that fills a room. But why does motion become light? Why does pushing electrons through a wire create something your eyes can see? And why do different lights look different? Some warm and yellow, some cold and blue. The answer is not just about wires and power plants. It is about the deep behavior of matter itself. It is about how atoms store energy, how they release it, and how nature turns invisible motion into visible color. Once you see the connection, a light bulb stops being ordinary. It becomes a window into how the universe works at the smallest scale, where movement, energy, and light are all part of the same story. Let me start from that question again. You flip a switch, and suddenly the room fills with light. It seems instant, effortless, almost like magic. But if I pay attention closely, there is a whole hidden story in that tiny glow. Electricity is moving. Invisible charges are flowing inside wires, carrying energy from one place to another. That energy doesn't just sit still. It travels, it bumps into atoms. It shakes things up, and eventually it becomes the light I see with my eyes. I want to start with the simplest idea: electricity is motion. It is not a substance like water or air. It is the motion of tiny particles called electrons. Inside every metal wire there are trillions of atoms. Each atom has a center and electrons moving around it. Most of these electrons are tightly bound to their atoms, but metals are special. Some electrons are free to move. They are not locked to one atom. They can wander through the whole material. These are the electrons that carry electricity. Think about it like a crowded room full of people passing a ball. The ball moves quickly across the room, even though each person only moves a little. That ball is like an electron carrying energy. The people are like atoms mostly staying in place. When I connect a battery or power source to a wire, it pushes these electrons along. The push is called voltage, but really it is just pressure, like the pressure that pushes water through a pipe. Here is the interesting part. Electrons don't race through the wire like bullets. Each one drifts slowly, bumping into atoms over and over. Every collision transfers energy. That energy makes the atoms vibrate more. And vibration is what we call heat. So electricity flowing through a wire first turns into heat. The wire warms up. The filament in a bulb gets hot. That is the first step of turning electricity into light. But heat alone does not explain the glowing wire yet. I need to think about the atoms themselves. Atoms have electrons arranged in levels like steps on a ladder. When energy enters an atom, an electron can jump to a higher step. That step is unstable. The electron wants to fall back down. When it does, the energy has to go somewhere. Sometimes it becomes more motion, more heat. But sometimes it leaves as light. Now imagine a thin wire inside a bulb, the filament. Electrons drift through it, bumping into atoms, heating it more and more. The filament gets extremely hot. Trillions of atoms vibrate. Trillions of electrons jump between energy steps. Each jump releases a tiny burst of energy as light. One jump is almost nothing, but together they create a steady glow that fills the room. Color comes from energy too. A slightly warm wire glows red, hotter, and it turns orange. Even hotter, yellow or white. Extremely hot, and it can look blue. Higher energy jumps make higher energy light. That is why the filament glows different colors as it heats up. I've seen this effect with heated metal in a fire or a stove coil. Red first, then brighter, then almost white. Temperature controls the color. Now here is something subtle. The electrons drifting through the wire are not the same ones releasing light inside atoms. Energy moves through the system. Matter mostly stays put. Electricity is the traveler. Matter is the pathway. Energy flows, transforms, excites, and escapes as light. Flipping the switch feels instant, but the story is happening very fast inside. Electrical energy becomes heat. Heat excites atoms. Excited atoms release energy as light. That is the chain. Resistance is another key part. It is like friction for electrons. If the wire had no resistance, electrons would move freely, nothing would heat up, nothing would glow. Resistance allows energy to transform. Too much current and the filament overheats, melts, or breaks. Even failure tells a story about energy moving through matter. Let me pause on that for a moment. Think about the filament again. It is incredibly thin, but it can survive very high temperatures for a while. The collisions inside are constant, chaotic, random, but together they produce a steady glow. The filament is like a tiny theater of trillions of atoms performing a synchronized dance of energy. Each atom's vibration and each electron's jump contributes to the whole spectacle. Here is another layer. The process feels continuous, but at the atomic level, it is a series of discrete events. Electrons' jump energy is released in packets. Those packets, called photons, travel through space until they reach my eyes. That is light. Each photon is tiny, invisible alone, but together they flood a room. So let me summarize this part quietly in my mind. Electricity pushes electrons. Electrons collide with atoms. Atoms vibrate. Temperature rises. Electrons inside atoms jump energy levels. Photons escape. That is electricity turning into light, step by step. What fascinates me even more is how fast it all happens. The moment I flip the switch, energy moves almost instantly. The electrons themselves drift slowly, but the push spreads at near the speed of light. My eyes perceive it immediately, but inside the wire, a microscopic drama is unfolding, and it does not stop there. If the current is too strong, the filament cannot handle the vibrations. The atomic structure breaks. The filament melts or burns out. Even the failure is part of the energy story. It shows how delicate and precise these transformations are. I have to point out something curious. Electricity and light are connected in a deeper way. Both are forms of energy, just expressed differently. Moving charges create electromagnetic effects. Light itself is an electromagnetic wave traveling through space. So when electricity becomes light, it is really energy changing its form, traveling from the world of moving electrons into the world of waves that my eyes can detect. Every glowing filament is like a tiny window into a universe of energy. Electrons drift, atoms vibrate, photons fly. The simple act of flipping a switch connects invisible charges to my perception of light. That is both ordinary and extraordinary at the same time. And here is the thing, this is only the beginning. I understand now how electricity becomes heat, and how heat prepares atoms to release light, but there is more to see. Different materials behave differently. Some release light more efficiently. Some change color in surprising ways. And there is a hidden dance inside atoms that determines the quality, brightness, and hue of the light. That hidden story is where real curiosity lies. That is what I want to explore next. How heat inside atoms turns into precise colors of light, and why some bulbs shine differently than others. That is the next step of this journey, and I can already feel how surprising it will be. Let me pick up from where I left off. I just explained how electricity moves through a wire, heats the filament, and excites atoms so that they release light. But I want to focus now on what happens inside the atoms themselves, because that is where the real magic of color and light happens. Every atom is tiny, but it has a structure that makes it behave like a miniature solar system. There is a dense center called the nucleus, and electrons moving around it in certain allowed energy levels. You can imagine these levels like steps on a ladder. An electron can stand on one step or another step, but it cannot exist in between. That is one of the peculiar rules of nature. When the filament gets hot, energy flows into these atoms. The energy can make an electron jump up to a higher step. It's like giving a person enough energy to leap onto a higher stair. But that higher step is not stable. Eventually, the electron falls back down. And when it falls, the extra energy does not disappear. It escapes as light, as a photon. Think about that for a moment. A single photon is tiny, invisible to the eye, but it carries the energy that was stored in the electron. In a filament, there are trillions upon trillions of atoms, trillions of electrons jumping up and down. One tiny photon at a time adds up to a continuous stream of light that fills the room. And here is something that always surprises me. The color of the light depends on how big the energy jump is. Small jumps release low-energy photons, which appear red to our eyes. Bigger jumps release higher-energy photons, which appear blue or white. That is why a slightly warm filament glows red, and a very hot filament glows white. It is all about the size of the jumps inside the atoms. Now, let me pause and imagine this from a different angle. Heat is just the vibration of atoms. Atoms vibrate faster as they get hotter. But inside each atom, electrons are also vibrating in their own way, jumping energy steps. So a glowing filament is not just a hot wire. It is a symphony of vibrations at two levels. The overall heat of the material and the individual energy changes of electrons inside atoms. Both are happening at the same time. Both are part of the light we see. This explains a lot about different kinds of light bulbs. A traditional filament bulb works because the wire can withstand very high temperatures. The hotter the filament, the more energetic the jumps, and the whiter the light. But modern bulbs, like LEDs, use a different trick. Instead of heating a wire until it glows, they use special materials where electrons can jump energy levels directly when electricity passes through. When the electrons fall back down, they release photons efficiently. That is why LEDs can produce bright light without getting extremely hot. It is fascinating to think that both methods, hot filaments and LEDs, are doing the same basic thing. Electrons are jumping energy steps, releasing photons. One uses heat as a middleman, the other does it directly. But the underlying principle is the same. Energy moves, electrons jump, light escapes. Now let's think about color more carefully. Different materials have different energy levels. That is why sodium vapor lamps glow yellow, neon lights glow red-orange, and blue LEDs glow blue. The specific structure of the atoms determines the energy jumps, which determines the color of the light. It is like each type of atom has its own musical note. The light we see is the note produced when electrons jump and fall. And here is something that always amazes me. Even though light looks smooth and continuous to us, at the microscopic level, it is made of discrete packets called photons. Each photon carries a precise amount of energy determined by the jump inside an atom. When billions of photons fly together, our eyes perceive a steady, continuous glow. But at the tiniest scale, it is a series of individual events. Now let me connect this to what happens in your eyes. When photons enter the eye, they hit cells in the retina that are sensitive to certain energies. These cells react chemically and send signals to the brain. The brain interprets the signals as brightness and color. So the glowing filament is not just energy traveling through metal. It becomes a signal inside my brain, letting me perceive light. Energy travels from invisible electrons in a wire, through atoms in the filament, through photons in space, and finally as signals in my nervous system. Let me think about this chain of events. Electrons drift, they bump into atoms. Atoms vibrate. Electrons inside atoms jump energy steps. Photons escape. Photons travel through space. Eyes detect them. The brain builds an image. A simple action, flipping a switch, is really a cascade of transformations connecting microscopic motion to human perception. And there is more. Light can behave in ways that are almost counterintuitive. It can scatter, reflect, bend, and even interfere with itself. But in the context of a bulb, most of that complexity is hidden. The photons escape in many directions, filling the room with a soft, even glow. The chaos of individual electron jumps and atomic vibrations becomes the order of continuous illumination. Now I want to think about efficiency. Not all energy that electricity provides becomes visible light. Some of it stays as heat. That is why incandescent bulbs feel hot. The filament is releasing a lot of energy as infrared light, which we cannot see, and some as visible photons. LEDs and fluorescent lights are designed to channel more of the energy into photons we can see. That is why they feel cooler and use less electricity. Here is a question that always catches me. Why do some materials release light efficiently, while others don't? It comes down to the structure of the atoms. Some structures allow electrons to jump and release photons easily. Others trap energy in vibrations or collisions, turning it into heat instead. That is why tungsten works for filament bulbs. It can survive high temperatures, and its atomic structure releases light reliably before the wire melts. And think about temperature again. Heat excites atoms. Hotter atoms make higher energy photons. That is why the filament changes color as it gets hotter. It is all microscopic electrons jumping energy steps. Color is energy made visible. It is energy leaving one level and becoming something our eyes can perceive. Now here is something even deeper. Light itself is part of the same phenomenon that moves electrons. Electrons in motion create electromagnetic fields. Light is an electromagnetic wave. So when electricity moves through a wire and excites atoms to release photons, it is really energy changing form within the same family of physics. Electrons, atoms, photons, they are all connected manifestations of energy. Let me pause on that. That connection is beautiful. A glowing filament is not just a hot wire. It is a bridge between moving charges and electromagnetic waves. The wire and the atoms are like translators, turning invisible motion into something my senses can detect. And that bridge is happening constantly, trillions of times per second. Even the temperature of the filament tells a story. Too cold and the wire only glows dim red. Just right and it glows bright white. Too hot and the filament melts. Nature sets boundaries on how energy can transform. Within those boundaries, the dance of electrons and photons creates the light I see. And every time I watch this, I realize that light from a bulb is not trivial. It is a window into the microscopic world, a glimpse of energy transforming in real time. Every flicker of light is a record of countless atomic events, and my perception of it is the final step in that chain. That is the end of part 2, where I explored how heat excites atoms, how electrons jump energy steps, how photons are released, why colors differ, and how efficiency and material structure play a role. Part 3 will build on this and show how modern lights like LEDs work differently, how energy travels more efficiently, and it will take us to the deeper connection between electricity, light, and perception, ending with wonder about the hidden physics in everyday life. Let me start from where I left off. I just explored how heat excites atoms, how electrons jump between energy levels, and how photons escape to create the light I see. But there's a twist I find fascinating. Modern lights, like LEDs, produce light in a way that doesn't require heating a filament to white, hot temperatures. Traditional filament bulbs are like a crowded dance floor. Electrons bump into atoms, the filament heats up, atoms vibrate, electrons jump energy steps, and light is released. It works, but it's messy. Most of the energy becomes heat instead of visible light. That's why the bulb glows hot in my hand. LEDs do something clever. They don't need heat to make light. Instead, they use materials called semiconductors. In these materials, electrons can jump across a barrier called a band gap. When an electron falls from a high energy state to a lower one, it releases energy as a photon. The process is controlled, precise, and efficient. Less energy wasted as heat, more transformed into visible light. Think about it like this. The filament is like heating a crowd until they throw balls out the window. It works, but it's chaotic. An LED is like handing out balls to each person and telling them exactly when to throw. Controlled, efficient, elegant. And the photons behave exactly as they always have. The color of light depends on the energy of the electron jump. By designing semiconductors with specific energy gaps, engineers can make LEDs glow red, green, blue, or any color. Combine them cleverly, and they even produce bright white light without the extreme heat of a filament. Efficiency is the key. Energy is never free. In a filament bulb, most energy is wasted as heat. In LEDs, the energy goes almost entirely into photons my eyes can see. That's why modern lights are cooler, brighter, and more efficient. Now, stepping back, I realized something profound. Electricity, light, heat, and atomic behavior are all connected forms of energy. Moving electrons generate electromagnetic effects. Light itself is an electromagnetic wave. When electrons flow in a wire and excite atoms, photons are released. Those photons travel across space and enter my eyes. My brain turns them into perception. Flipping a switch is a chain of transformations that connects the invisible microscopic world to my conscious experience. Every photon from a bulb carries a story. It began as energy somewhere else. A flowing river in a hydroelectric dam, sunlight captured in solar panels, chemical energy in a battery. That energy traveled, transformed, and finally became visible. Every glowing bulb in my room is a record of that journey. Color is even more fascinating. Blue photons carry more energy than red. The jumps inside atoms determine the photon energy. Human eyes detect only a small range of this electromagnetic spectrum. Infrared, ultraviolet, and beyond are happening all around me, invisible, yet part of the same energy dance. And light itself is extraordinary. Photons can scatter, bend, reflect, or interfere. But inside a bulb, this complexity becomes a simple, steady glow. Chaos at the atomic level becomes order for my eyes. Trillions of electrons and atoms performing countless jumps result in a continuous stream of photons filling the room. I have to think about perception again. Each photon that enters my eye hits a cell in the retina. Those cells react chemically, send signals to the brain, and my mind interprets them as color and brightness. The glow in the room is not just physics, it's physics meeting biology. Electrons, atoms, photons, eyes, brain. A single switch connects the microscopic world to conscious experience. Different materials tell different stories. Sodium lamps glow yellow. Neon glows red. Blue LEDs glow blue. The difference is atomic structure. Different allowed energy jumps, producing different photons. Every type of light is a miniature atomic orchestra performing in invisible harmony. Temperature still plays a role. Incandescent filaments must reach thousands of degrees to produce white light. LEDs can produce any color at much lower temperatures. Two approaches, same principle. Energy moves, electrons jump, photons escape. It is all variations on the same theme. And here's what strikes me. Electricity and light are not separate phenomena. They are the same family of energy behavior. Moving charges create fields. Fields create photons. Photons travel. My eyes detect them. My brain perceives them. Every light I see is a bridge from microscopic energy to conscious awareness. Now for the conclusion, the part that lingers in my mind. Every time I turn on a light, I am witnessing an incredible chain of events. Invisible electrons move. Atoms vibrate. Electrons jump energy levels. Photons are released. Those photons travel and enter my eyes. My brain interprets them as color and brightness. Ordinary light is extraordinary. Every photon is a messenger. It carries information from the invisible microscopic world into my perception. Each glowing filament, each aditi, each ray of sunlight is a story of energy traveling, transforming, and connecting worlds. I walk through my illuminated room, and every corner is a reminder that the ordinary is actually a gateway into the deep, hidden structure of reality. Light is everywhere. Electricity is everywhere. Energy is dancing constantly in ways I can barely imagine. And knowing the story behind even a single bulb makes me wonder what other ordinary things around me are doors into hidden worlds. What invisible dances are happening all around me, unnoticed, waiting to be discovered. The simple act of illumination is a profound link between the microscopic and the conscious, the hidden and the seen. And once I see that, I realize that light is not just something I observe. It is a connection to the unseen, a bridge from energy to awareness, and a never-ending invitation to curiosity.